Hello everybody, welcome to Skyter Livestream. It is I, Marc D'Antonio, the hacked one, the man without a Facebook. They took it down and said it was a meta copyright infringement. I've never had copyright infringement, ever. So I have no idea what that's about. It's a bald-faced lie. And just to get it out of the way, I lodged a formal complaint with the California Attorney General this afternoon. So we'll see if that gets my account back. It's still out there, but they said it's copyright infringement, so I don't know how long it'll take, but it better not take too long. But as you can see, it doesn't affect the important stuff. This is it right here. It's good to see you guys. Welcome to everybody that's here. I see everybody that's out here. We got Michael Hedrick was the first one. Hey there. Cosmic Ray. Nice to see you guys. And we have C&D Boy Petita. How are you? And Daryl is with me too, by the way. And if, in case you want to know that for sure, Daryl, say hi.
Hi, Daryl.
There you go. Yeah, and we are doing our best here to make the best of a bad situation with the Facebook side. But as you can see, the telescope is just performing wonderfully. We have a just past first quarter moon out there right now. And look at the Lagoon Nebula, which, by the way, is kind of near the moon. Let me bring up our thing here. So there is, let's back out. There's where the telescope is. All right, and if we back out just a little more, okay, there's where the moon is. All right, it's very bright in that region of the sky, but because of our filters and because of our new camera, we actually have a really nice view of the Lagoon Nebula. We have twice the resolution of the previous camera. This camera is what's called a ZWO ASI 183 MC Pro. Now the 183 is the number. MC means that it's color. MM would have been monochrome. And the Pro means that we have additional capabilities. If you notice in the Lagoon Nebula here, we've got this extra detail that we've just not really seen before. And also this camera allows us to do something even cooler. Watch this. Now, watch what I do here. I'm gonna drop down this bar right here, and we'll show you right into the heart of the nebula. We can see this hourglass in here, and it's the star that's in this hourglass area right here that's actually bright, causing this entire nebula to glow at the moment. And this is an O-type star, a very, very hot and blue star. And it's the reason why the Lagoon Nebula glows. That star is also destined to go supernova, at which point there'll be some further ionization of the hydrogen gas in the region and probably oxygen as well. And when that happens, one of the things that we'll probably see is that this nebula is going to change drastically from the day it actually goes supernova. This nebula will actually change quite drastically, because that star is doing a lot of the illumination. A lot of the glow is caused by that star.
It'd be interesting to see the light echoes as the wavefront moves through the nebula.
Like in supernova 1987A, down in the Large Magellanic Cloud. That supernova, you saw the expanding ring of light coming out. It was amazing how that happened. You know? So, this is the Lagoon Nebula near the moon. And we're photographing it tonight because we can. And this is a good target to show you guys the quality of the new camera. And the nice thing about this is that we are at 32%. If I go to 100%, that'll be like the maximum. And this right here, this is the natural resolution. Look at the detail in all these little tiny clouds. This is something that was unavailable to us with the last camera. And now it's available to us, and it just showcases itself. If you saw before my Facebook site got ripped apart, if you saw the Messier 33 in Triangulum, the Galaxy, and if you saw the Cygnus section of the North American Nebula that I put up. Absolutely stunning images, and I just thought it was phenomenal. Really, really cool. So we could play with the settings here to actually darken up and get us some more contrast out of this. And as you can see, it really shows all this tremendous tiny detail. Really, really cool. And this, of course, you can see here, this is a dark clump up here. That dark clump right there is a self-condensing, gravitationally condensing cloud of dust and gas. And it looks like it has a tail on it, probably because there's stars around here that might be pushing that material back, or this whole cloud might be moving in this direction, leaving a tail behind it as it goes. We can't see the universe in motion because it moves much more slowly to us because things are so far away. But is this not the most incredible thing? It's really pretty. Hello, Suzette Bavier, how are you? Alicia Vieras, how are you? Nice to see you. Cindy Murphy's with us. That's good. Hi, Cindy. Sam S. said before he's looking forward to seeing the stream. And here we are. This is our Lagoon Nebula. You can see lots of detail. Look at that beautiful tentacle cloud. That's just incredible. This is a cloud that's shaped in part by the stellar winds from stars in this region. The O star powering it is inside here. And as I said before, we can actually reach that with this camera like that. Check it out. And then you can actually see the convolutions and the pillow-like appearance of the inside of the nebula here. All right, and this is just stunning. Again, something that was not reachable for us before. And so here is 141% zoom, and you can still see some appreciable detail. So we're really, really happy with this camera. All right. That hourglass figure right there, that actually is the shape due to the O star that's powering it. Okay, and I think this is the O star this guy right here, Daryl? Do you know, or is it buried inside the cloud?
I believe it's actually buried inside the cloud.
Because it looks like the light is too regular, so it looks like it should be behind it. Hey, Fantasy, what's up? Renee Behrens, hello, Renee. Nice to see you. That's Alicia's mom. All right, let's see what it wants to set for our lighting. As you can see, it goes crazy. It tries to pull all the detail out that it can. And if we back out, you'll actually see that this nebula is, of course, very extensive. This is in Sagittarius, and we'll color correct because it's got a little too much red in it. There you go. Now you can actually see the real red clouds that are around here. And if you remember, off to the left here, a little further than these controls here off the screen, that's where the Chinese Dragon Nebula is located. So we're going to save this right now. All right. And we'll save it exactly as seen. And why don't we actually go over to the Chinese Dragon Nebula and check it out? Because yes, it's stunning, and there's a lot going on here. Thanks, Suzette. That's an excellent way to state it, too. It is stunning. Okay, Papa Tom's with us. Hey, Papa Tom. Nice to see you. Okay, so this has been saved, and it's going up to the server right now. And the photo that's up there is this one right here. This is the actual photo that's going to be up there. Look at the difference between this and what we've done in the past. It is just absolutely incredible. All right, we'll take that out. All right, and now we have this. What we'll do now is we're going to head over, just go to the east a little bit and head to the Chinese Dragon. All right. And here is our view right now. And we'll just, this is a 1 second shot. And we're just going to head over to the east now. And we're going to just tell it to go to east. You'll notice also that east is now east. And things are going the right direction. Corrected that as well. And actually, Terra corrected that out there. All right, and let's go over here. I'm not quite used to the size of the field yet. Our field is now just 1.5 degrees wide and a half degree tall. So it's a lot less than it was, and that's good because we have shrunk the field of view but put more pixels in there. So we've effectively doubled our resolution of our camera. Starlink, there it goes. It's a streak because we're doing a 1 second exposure, so it's actually going through the field of view. All right. I think it's a little north of me now. So we'll head up there now. Okay. All right, I'm just going to take well, actually, I'm all aligned, so I can just go here and see how close I am. All right, let's go and move over right here. Yeah, we're close. Look at that. Ooh, the Trifid would look good tonight too, probably. Oh, yeah. I'm so excited. This is just so cool. Did I get it right? Oh, look at that. Looks like I got it almost exactly where I wanted it. I gotta go up just a little more. Just a little more.
Curtis Horn asks what camera you're using.
Hey, Curtis. We are using a ZWO ASI 183 MC Pro. It's a new addition. We added it several weeks ago, and I just got back from there. I was there just since Tuesday of this week, and I got back yesterday. It was just a quick trip to collimate the telescope because it was out of collimation. And thanks to Tara and Marianne, who had gone out there earlier, they were able to actually get it into a position where the collimation was only an hour of time. Normally, collimation can take many hours, especially with an F2 system, because it does. Right.
Collimation is a royal pain, let me tell you.
Yeah, well, you collimated lasers for years.
Oh, yeah. Well, lasers, telescopes.
Yeah.
You name it.
Auto headlights. All right, we're gonna focus on this section here. Okay. By the way, hi, Curtis. I didn't say hi to you, I don't think, but I answered your question. Yeah, so that's the new camera, Curtis. All right, let me come in here and first things first, I'm going to drop this down a little bit. Okay, that's what I want. I want to actually do that. That's what I want. Okay. All right. So we are guiding, as you can see right here. And 1.2, 1.4, 1.7. As long as it stays under 2, we'll be okay. So I have to let it settle out. And then I will start. It was a very successful collimation. If you remember, the stars weren't really quite focused. They were kind of donut-y and had little tails. And that's because the lens on the end of the telescope was cocked at a little angle. And that's a huge exaggeration. All right, let's take this and make it a 30-second shot. All right, so it'll be 30 seconds. And we'll come out of this, come back in and look at the lagoon one last time. There it is. And now we're heading to the Chinese dragon. We're going to see probably this little piece of it, maybe. I'm not sure. We'll find out in a minute. Okay. Hey, thank you, Michael, for inviting your friends. Everyone's invited to this, and it's rated G. All right, let's see what we got. Obviously, we have to adjust our curves. The red curve, the green and the blue curves are all misaligned, so we're going to first match up our curves like that, and then we're going to move our levels over so it's not just bright white, and now we'll see the data. And here is the data. Wow, look at that. Okay, so we're going to zoom out a little bit. Here we go. So here is this beautiful section right here. And as you see, we've got like a bluish haze. That's what little of the moonlight actually leaks in. However, we can correct that and get rid of a lot of that, and then do this. We can pull our level in, climb that white peak, and you can see the detail now showing up, and it will just get better and better and better. The more we stack, the better it gets. Remember what a stack is? We take a picture, then we take a second picture, align it with the first, place it on top, and we just keep building an image sandwich. And the more we do, the dark data and the light data come to the top and really, really show well. And that's what we're doing here. If I pull this down just a little bit, this is the mid-level, it'll just subdue the noise a little bit so we can actually see what's happening. There we are. Look at that beautiful little tendril that's developing now. I have to warn you, unless I actually get drop dead tired, I don't know when to quit with this new camera. I think, what'd you call me the other night, Daryl? You said something about, because I wouldn't stop taking pictures. You said you had to go to bed and I wouldn't let you. I said, no, you got to watch this. Something like that. Well, what did you say? I was incorrigible or something?
Oh, yes, incorrigible.
Well, hey, I mean, let's be fair. This new camera is delivering views that like we've never seen before, and I'm just so happy with this.
Yeah. Oh, the red thing always reminds me of like a koi, a giant goldfish in a pond.
It does look like a koi fish.
It's very pretty.
Yeah. Let's see if we can do this, and let's also... Here we go. That's nice. I just removed a little bit more of the moonlight because I want you to see this up here. Here's a red emission nebula with some tendrils of black reaching into it, and then right around the outside edge of it, you see a little blue. And this is all dark nebula here. All this is dark nebula. This is not a void where there's no stars. It's actually a black dust cloud that's hiding the stars behind it. Now, why are they black? Well, the reason that the clouds are black is because they're made up mostly of carbon and silicon atoms, and carbon, of course, is a dark substance. And you're getting carbon-carbon molecules, CC, bonded across them. And when you get those nice strong molecules, they will also build up with each other and make many, many carbon clumps out there. So it's like effectively kind of like coal, but not coal. It's particles. And they sometimes get held together by ice. And ice is obviously prevalent out there in many forms. We have ice that's made of water, okay, water ice like in this bottle. We have ammonia ices, we have formaldehyde, we have methane ice, we have carbon dioxide ice, and that will sometimes secrete onto these particles, and then now you'll have all these many, many millions of carbon atoms bunched together, and then a layer of ice over them. So you have these tiny little micron-sized dust particles that have a tiny layer of ice on them. And that ice is what, contains a lot of the substances like the hydrocarbons and other foundational elements of life, the building blocks of life on them. And so that's what the dark clouds really contain. And so it's dark clouds are where it's at. The dark clouds are where life springs. And the red nebulae are transient. In other words, they go away after a period of time, leaving just the dark clouds. And the reason I say that is because as stars are born, stars die. The hot young stars have a lot of ultraviolet radiation, and that stuff will cause the hydrogen gas that's also mixed in with the clouds here to glow. And that's what we call the hydrogen alpha emission. Kind of like my face, from my red astronomy lights in here. So when you look at that red glow is caused by the hot young stars. Those hot young stars will eventually die, go the way of supernovae perhaps. The younger the star and the hotter the star, the shorter it lives. So that O star that we saw over in the Lagoon Nebula, that's west of this, okay, that O star only has a couple million years left in its existence, and then it's going to explode in a supernova. And the entire nebula will then probably go dark in some ways, but the expanding light echo, as Daryl was talking about, will illuminate it and cause it to be illuminate the dust by the actual light moving out, and will of course ionize the hydrogen gas in the region for a period of time while it's this very hot star expands outward. And if it's a very, very hot neutron star, then that ionization could last for quite a while. But it's just something else. Look at how beautiful this is, Daryl. This is really something.
Oh, yeah.
Okay, we're going to zoom in on this a little bit now. Look at that. Wow. And the guiding is pretty good, too. The auto-guiding system is working well. I'm going to do this. There. Now you can see some convolutions here that have never been available to us before inside this nebula. Okay, remember I mentioned the blue up here? You notice how this dark cloud is rimmed with this blue? Okay. This blue is the dust scattering the blue starlight that's hitting it from stars in the region. And it scatters the blue light because blue light is very high frequency, and it's easily taken in and redistributed and sent back out. So that's the scattering process, and it's got a name. It's called Rayleigh scattering. It happens here in our atmosphere. The reason this is blue is the same reason that our sky is blue, effectively. Scattering by molecules in our atmosphere will cause the blue light to go every which direction and not come straight through to your eyes. And so everywhere you look, we have a blue sky on this planet. If scattering didn't occur, we wouldn't have blue nebulae like that one there that we're looking at right here. All right? And we wouldn't have a blue sky. If we had a clear sky, then our sky would be black and you'd see stars. If you could blot out the sun, you'd see stars around. Okay? If the atmosphere wasn't glowing from this scattering process of light that was flying around everywhere. So it's interesting, if the atmosphere was made of something different, like methane, then our sky wouldn't look this way. If the sky was, if the atmosphere was made mostly of carbon dioxide, well, then the scattering might look a little different, like on Mars. Now, the reason Mars' sky is pink is actually because of the dust that's picked up by the very high winds that can occur there. And the top layer of the dust on Mars' surface is like the consistency of talcum powder. And you know how easily that gets around. So that talcum powder dust takes a wind that's got to be somewhere around 90 miles per hour to actually lift it off the surface of Mars. That's because the atmosphere is so thin. Okay? So we have all the material that makes planets like Mars hidden in all these dark clouds. All right, and we see the physics occurring that causes the clouds to change color like we see here. These dark tendrils are shaped by shock waves moving through this material from past supernovae and from stellar winds and so forth. And that's what we're seeing in this region. It's just there's so many things going on in this region. It's incredible.
Marianne is here. Hello, Marianne.
How can she be here? She's kayaking down the Colorado River in the Grand Canyon.
Probably not right now. I mean, it's after dark there in the canyon. She says from the Grand Canyon, though.
Yeah, she's there. Yeah, excellent. Well, it's good to see you, Marianne. Yeah, this is beautiful. Look at this gorgeous reflection nebula. Let's zoom in on this a little bit, and then I'll play with it here a little bit to see. Okay, now watch. I'm gonna actually kind of remove some of the noise here. Ready? Okay, we'll cut the noise down a little. Let's go all the way down just to see what it looks like. Okay, it'll pop in a second. Yeah, see, with the old camera, we wouldn't have any of this available to us. This is amazing. I want to thank you guys for coming out and spending this time, too. No, I'm not done. For those that tried to send me Facebook messages, I'll just say it again. I had a message that greeted me this morning in Facebook that said, Meta copyright infringement. And that was my ID. And I have no idea what it is. And my Facebook profile was taken down. So 10 years worth of material's all gone. Now, I can probably get it back, but not to mess around, I've already lodged a formal complaint with the California Attorney General. Today I did it, and so it's on record. So the Facebook people are going to have to keep my data around because I've lodged a complaint that this was done illegally. And they only give you 30 days before they'll delete the account if you can't get it back in that time. And other people have been saying that to get their accounts back when this kind of thing happens has taken them sometimes 2 months. Well, we don't want that to happen here. I need to have my account back because I get a lot of opportunities through Facebook, and I'm not going to tolerate being kicked off because somebody decided I committed a copyright violation. Why? Because I'm probably showing these things, and they think these are copyrighted. They're mine. I created them, and you don't even get the chance to explain that. So I'm really unhappy about that. Oh, Renee Cruz is talking about the great filter. You go, Renee. That's good. Oh, look at that. Wow. So let's back out here, and now you can see a little more. All right. You can see the blue rims here and down here in this reflection nebula. There's more down here. So there's a lot of scattering going on as well. Nice. Wow, there's actually modeling in here that we've never seen before. Wow. Well, here, that's the Chinese dragon. That's fantastic. We're going to spend a lot of time probably re-photographing many of the things we've done because we now have literally twice the resolution. I mean, I'd be a fool not to. Hello, Desert Dweller. What's going on? Rocket City, what's happening? Marianne asked, how did that even happen? I don't even know. It was fine last night, before I got on the plane out of Phoenix. It was just fine. I was on it, in fact, getting stuff, looking at things. I got home, and I got home around midnight here in Connecticut, and it was already gone. And I have no idea what happened. I don't put copyrighted stuff up on my page. I just don't. Ray says, you've been canceled. Okay, well, we'll see just how well that works. Because in the same way that I found the perpetrators that stole my credit card when I bought an iPhone from an operator down in El Paso. I found everything they bought. I found all the managers of the stores, talked to every one of them, and I even got video of them stealing or trying to buy a PlayStation at a store, and they did this all within 20 minutes. I had all this data within 3 hours. And I called the El Paso detectives, and I gave them all the information, and I said, now go get them. They said, well, it's not $10,000, so we're not gonna. I said, you mean they get away with it? And he said, yes. And I said, oh, well, if I come down there, can I kill them? I'm going to come down and kill them, okay? Because let's remove them. They're cancers on the planet, you know, these thieves. So I'll remove them. I'll kill them. Is that okay with you? I said that to the detective. And he said, well, I kind of advise you not to do that. Now, he knew I was being, you know, tongue-in-cheek. But I said, but would you stop me if I did? And there was a long silence, so I didn't do it. I'm not that kind of person. But, you know, it gets you irate, you know. Wow, this is beautiful. Chinese dragon looks great, Daryl. All right. Let me just pull one little... let's do this. I'm going to adjust the colors here. One more little click. Okay. All right, we'll save it like this. This is 32 stacked images. Look at the modeling in here. This is going to show so beautifully. Wow. This Sky Prison Tour. Haha. Oh, Ray. Living up to the curmudgeon title. He's alright. Okay. We got that. Any ideas? Oh, I know where I want to go. I want to go to the Trifid now. Trifid Nebula. Alright, let's do this. First, let's go back to our little night vision mode here. Here we go. All right. What do you think, Daryl?
You did save that, didn't you?
What? Oh, yeah.
Okay.
Yeah. So we're going to go to the Trifid now. I have been dying to get a really good shot of the Trifid Nebula. After all that has happened with this camera and everything. Here it is. Ray says, curmudgeons are us. All right. Now let's go south a little bit. Bring that up into the view a little more. I'm going to try and keep this cluster in. I am going to do an autofocus one more time because I had done that before. And it looks like it's fine, but the stars in here, there's actually 2 stars in here. And let's go check those out here. You can see them right here. Watch. I zoom in. Okay. And you can see they're just a little bit out. So I'm going to take our focus and run it again.
Well, it's cooling off at night, even in Arizona.
It's 27 Celsius out there right now in the building.
Maybe turn your T-comp on.
Yeah, I'm going to try that, but I'm going to first I may have to redo the T-comp with this camera. Okay, there we go. See the donuts? When you take a star out of focus, you can actually see the color much better, guys. That's one reason why you might actually want to defocus stars, is to show their color. All right, so now we're gonna scan in, and we will see. Now, if you're good at you read these numbers over there. Okay, the current score for the roundness and tightness of a star image is at 10.6. The best was 6.5 earlier, so we're gonna see if we can do better than that. We should be able to get it under like around 5.
What is that? Arc seconds?
It's I think it's a percentage actually. So watch this now. This should. Oh yeah, Starlink. Thank you. Okay, there's 5.9, 5.7, and then it starts going up again because it's on the other side of the curve. See, it's gonna build a curve, and then it's gonna interpolate mathematically where the center is, and that's the value we're gonna go to. I could have told it to go in smaller increments, but that would take a long time to do this. So this is getting us close. So right about now, we're going to see that. There it is right there. That's our center line. Hello, Gladys. Oh, I wanted to acknowledge that Alicia Vieira sent me the coolest little voice message from her daughter, Darlene, who I think is the cutest little astronomer you ever met. She's 10 years old, and I knew her when she was 9. And she has my book, and she was actually talking about some astronomy and left a nice voice message. It was the funniest thing. I liked it. But I wanted to acknowledge that in case she's listening.
Alexa said Darlene got a telescope.
Oh, that's right. I was going to tell you that. I forgot. Yeah, her uncle gave her a telescope. That's it. I was 9 when I got my first telescope, and that's when I decided to be an astronomer. Look how sharp and clear those stars are. All right. Okay. Let me actually pop that back in and dock it and then get rid of it because we don't need the focus thing in there right now. Okay. Now, let's do our shot. You know, technically, if you want to do a good job, you need to focus every time you go to an object. And I've been avoiding that. So we're going to see how it works. All right, 30 seconds underway. Trifid Nebula. All right. And what did we have before? We had the Chinese dragon. And this is what's in our buffer. Look at that beautiful Chinese dragon nebula. That's really stunning. Wow. Okay, well, it's up there on the server as we speak. Hey, C&D boy, what's up? Renee Cruz, nice to see you. Here comes our first Trifid Nebula image. Let's see if it's stable. Oh, look at that. Wow. Wow. That's a good image. It just needs to be little more, get rid of some of the blue. Okay. And let's darken this up. So we darken it up, and the magic happens. You can start to see the other red nebula around it. Here we are. Bring this down. Oh, look at that. This is already the best Trifid we've ever done. You can see these beautiful blue reflection nebula, as we call it. Again, done by scattering. And we can actually bring this way down And you can see a little more saturated color in there, see? You can see some beautiful little subtleties in here. We've seen that before, but we're going to be able to see it a lot better with this particular camera. And already we can see that the blue's going all the way around, Daryl.
Well,
you can see that. The way I think this is, it's like you got this in the middle, you've got this diffuse, or this emission nebula, roughly spherical around the hot stars in the middle there. Then you have these dark lanes of material that just happen to be bisecting it. And I think all around it, you have this dust that's doing this subtle reflection nebula. You can't really see the blue too much here, but I do believe it's there. But I don't think you can see it very well because it's a thin layer of dust, and the emission nebula is so bright relative to it. But if you look in here, all right, when we zoom in, you'll see that it's actually blue in there. Okay, so there, look at that. There's a bluish haze in here, and so that bluish haze that you see throughout, I think, is the overlying dust cloud that's involved here. This is very nice. Yeah, and then this will show you what's really there. Okay. But again, the moon is very close to us right now. So the fact that we can get any of this is actually kind of miraculous. Okay, so let's do that. If anybody has any questions, fire away. Very nice. A little color correction. So you'll notice in the past we saw the stark lines here that come through, including the overlying material that's also here. But what we didn't see before is the subtlety of these black tendrils in here. This is, again, due, like these little guys right in here. See these little subtle things right there? Those things are very, very different from what we've seen before. Right? We've got some right there. Okay, look at how this branches off. It goes up, comes down, and you got complexity right in here. That's amazing. And then you got this little tiny tendril sticking up there. Again, all this stuff is driven by the stellar winds up there that are driving it around and pushing it around. All right, and of course the dust itself comes from countless supernovae, where the dust is made in the outer atmospheres of these big supergiants, these red supergiants. And a lot of it's carbon, some of it's silicon, all right, and other dust particles and the ices that I talked about. Very, very cool. Michael Hedrick says, in my mind, I'm actually looking out my window into outer space from my magical seat. That's kind of cool. Well, if you think about it, a lot of people will put this on their big screen and then just sit down and eat popcorn and watch it like a TV show, which I think is kind of cool. Because I know that we definitely seem to have that appeal, you know. It's very cool. All right. If you want to see all these pictures, don't forget, you go to skytourlive.org right down there. Okay? Skytourlive.org will allow you to, it's our entry point into all things SkyTour. and you can see pretty pictures. You can go to the database directly and check out the images yourself. We teach you how to do that in the on the website, sketchalive.org. And then you can get prints, and the prints that you order are high-end, fully processed prints. You don't get the raw ones like here. We fully process the prints that you actually end up buying, and then end up on blankets and framed under glass, all that, or on mugs, cups. All that stuff is fully processed, highly processed. Noise is removed, colors are balanced. Everything is just done amazingly, precisely. So that's all good. And if somebody wants wallpaper on one of their rooms, we can talk about it. I had a doctor's office ask me about taking one of our large nebulae and blowing it up to wallpaper size, and turns out we can do it, which is really cool. It's called resample, and you build a much larger image. It looks really pretty. So you can start to see. Let me actually bring some of the subtle detail back in here. Okay, you can see more of a blue glow around this now. The primary blue glow is up here, all right? But there's a great deal here. You can see this beautiful. It's unmistakable. It's really pretty. Wow. Really gorgeous. All right, we'll take this to 17 exposures. We're at 16 now. And move on. There's so much more to see. I can't wait to do Thor's helmet with this camera. It's going to be bigger. We're going to see more detail. I think Izabela will be happy about that.
Oh, yeah. While you're in the neighborhood here, can you go back to Messier 22? It looked nice earlier.
Yeah.
It'll look even better now.
You can do that. It is right nearby, isn't it?
Yep.
Okay. So we're going to save the Trifid now. And we'll save it exactly as seen. Like that. Alright. And so that's on its way up to the database. So, or I should say, I'm sorry, the server. Okay. So going back to our 1 second shot here, we will now go into what we call our night vision mode. And let's now go back to Measure 22, as Daryl has suggested he'd like to see. And that's actually a really cool globular cluster. And it looks really good too. Alright. Off we go. Here it is. Look at that. Okay. This is going to be nice. Let me just quickly look at this. We're at 40% on our sensor right now, meaning 40% zoomed in, 100% is native resolution of the sensor. And that would look like this. Let's bring it up to that. So that's our native resolution. Looks like our stars are still in good shape. Alright, we're going to go back to, let's say, 50%. Starlink goes by. Alright, and let me just nudge our processor here. Make sure we get our guide star. It takes about 11 to 12 seconds to get a guide star. So you'll notice that it's actually sitting there for a minute. Now it's doing the guiding right there. You can see it. This looks like good guiding. This is going to be really good. So let's do a 25-second shot of this. When I say a 25-second shot, it's going to be 25 seconds per exposure. All right. So we can pop into our stack now, and we'll see the Trifid Nebula one more time. All right. It's just a little out of focus, and we always have trouble with the Trifid because it's not out of focus. It's streaked because the winds may be growing out there. By the way, when I was walking into the observatory the other day, this past Wednesday night, hold on, let me see what we got here. Okay, it's a little bit windy. I noticed that as I was about to step into the building, I looked down. There was a spider web between the bottom of the door and the ground. And that spider web, that's better. That spider web had a little spider in it, and the spider was about, the size of a quarter. Okay, 25-cent quarter. And I looked closely, and I was like, I just saw my first black widow. She was building a web, and I think I disturbed her. So what I did was I spent the night just stepping over her to get into the building. I didn't feel the need to kill her or anything. So I just stepped over it and ended up doing everything I had to do. And there were no tarantulas this time. So, oh well. I didn't get to see any tarantulas. Okay, this will be about as dark as we want to go. Yeah, M22. Really pretty. And you've heard Daryl talk about M22 before, and if it was just a little farther north, how it might rival Messier 13.
Oh, yeah. Hello, Dee Dee. Long time no see.
DDB's with us. Hey, Dee Dee. Oh, about the spider. Well, black widows rarely leave their webs, so as long as you don't walk into the web, you're okay. You know, they're not like ground hunters like a tarantula. You know, we had a tarantula the size of my hand actually in there a few months ago, and the tarantula was very docile. In fact, one of the people there, Tara's husband, whose name is Dale, he actually reached down and let it walk up on his hand and down the back of his arm, and then he walked outside and kind of gently brushed it off. They don't want to bite. You know, they're very docile. That's why people have them as pets. You know?
It sure has some fearsome-looking teeth, though.
Their fangs are
fangs?
A quarter-inch long.
Oh, yeah.
They can deliver a nasty bite. And Michael wants to ask a question. Yes, please go ahead, Michael Hedrick. Ask a question. Okay. Let me pull this down even more. Fully resolve this now. This is really pretty. Alright. We're going to just drop the red out of here a little tiny bit. There we go. It's a little better. There we go. I was going to ask about the gravity field of this versus if it were just one big star. Well, this cluster is light years across. So if you consider that if this was one big star, then this would be a star that's many light years across, and that we haven't seen in the universe as of yet. No, I don't expect we will.
There are hundreds of thousands of stars in this cluster too.
Yeah, So the mass would have to be stupendous. He says, but then I got so blown away with all the details of the image, I lost my train of thought. Yeah, okay. Daisy and Zoe, did I say hi to you? I am so sorry if I didn't. I apologize. I should be punished. I am, see? I'm like Max Headroom. Oh, hey. Okay, so we've done 10. That's good for this. M22. And it's a globular cluster, which is really pretty. Save it exactly as seen. Very nice. All right, Daryl, you got yourself M22.
Thank you.
Oh, yeah.
Elisha, Darlene, yes, there are different kinds of clusters, star clusters. What we just saw is what's called a globular cluster. They can be thousands to hundreds of thousands to millions of stars, all in a more or less loose or tight ball shape, hence globular cluster. There are also what's called open star clusters.
Yeah, we'll show one of those.
Okay, which are generally, it might be scores, 50 or 100 or several hundred stars in an open cluster.
Yep.
Globulars are very different than open clusters. Globulars are some of the oldest objects in the universe, have some of the oldest stars.
Yep.
They date back to not long after the Big Bang. And open clusters are generally much younger. When we see, like the Pleiades or the Hyades, the double cluster in Perseus, stuff like that, those are open clusters. And they don't stick around a long time. They can sort of drift apart over long time scales.
Yes.
Globular clusters are big enough that their self-gravity holds them together, and they've lasted for billions of years.
But they do pass through the disk of the galaxy because they're actually called halo objects. They're outside our whole galaxy on orbits of their own, and they will go plunging through the disk of our galaxy on occasion. And that's actually something that's a fascinating topic, because I think that, I would guess that they would shed some stars or gain some stars as they did so. So, to answer your question further, Darlene, we just saw that globular cluster. This is now a loose cluster. This is looser. See, it doesn't look like that globular. The stars aren't packed. They're actually kind of looser. This is an open cluster. This was formed in a gas cloud of hydrogen gas way in the beginning. And most of the stars in here are all the same chemical composition. I know you don't know what those words really mean yet, but they're made of all the same things because they came from a cloud that was made of one particular set of things. So all the stars made out of it will be made from the same things. And that's what we're looking at here. So this is just a beautiful cluster. Let's actually let's do this. Let's actually take a shot of this. All right, this is NGC 6647, I believe, and we'll do a 25-second shot of this.
Now, when we had Messier 20, the Trifid Nebula,
yes,
in the field, there's actually a nice open cluster just above the Trifid, which is the Trifid is Messier 21. The Trifid is Messier 20. And Messier 21 is an open cluster just above it.
Yeah.
And then here, we're not too far away from them now with Messier 22.
Mm-hmm.
Globular. All these are in the constellation Sagittarius.
Yeah.
Which is basically, the richest part of the sky.
That's right.
You'll see many of the Messier objects are actually in and around Sagittarius.
Okay, so here is that open cluster. Now, yes, there's lots and lots of stars around here, and You know, remember the universe is in 3D, so that it looks like they're all right next to each other. But if you turn sideways, you'll see that some are forward and some are out back. Okay, so this cluster is probably closer to us than the Milky Way stars that are behind it. So that's one of the things to keep in mind here. But this is just an example of what's called an open cluster, because it's more open than a globular. Although with a telescope like this and a sky like this, it's hard to differentiate the cluster sometimes. You know. Darlene says the open clusters would be like liquid or gas. I'm guessing she's talking about atoms. I'm trying to get into her mind and think about what she means by that. Well, ask her, Alicia, what she thinks globular clusters are then, and let me know.
I suspect she's thinking density.
I was thinking maybe, but let's see what Alicia says.
Gas versus liquid versus solid.
Yeah. Hey, Michael. Michael Galea is with us. How you doing? Yeah, this new camera is just stunning. She thinks they're like solids. Okay, I see what you're saying. All right, you know what? Good analogy, Darlene. If you think of a globular cluster, and sort of like what you were saying, Daryl, kind of a solid ball, and this is sort of like a ball that's kind of blown up and kind of scattered. Makes sense. All right, makes sense. So you can think of the globular cluster as the actual beehive, you know, the hornet nest, and the stars like this on the outside are all the bees around it. You know, they've left it, and they're just humming around.
Be cool. Careful how you frame that. The beehive is actually an open cluster.
I know that. I know. I wasn't trying not to make that distinction. Okay, so let's pull this down a little bit just to kind of isolate. Look at that. What a beautiful cluster. You notice this here, the stars look whiter than the background stars. There's a lot going on in this image, okay? This is more, I'm going to say this cluster is probably a lot closer to us than the background stars. Why? The background stars are reddened, and that's probably reddened by the dust that they sit within that's between us and them. And this cluster has little or less of that dust between us and it. So let's go in, that's my guess, let's go in here and let's look at this cluster and see what we can see about it. Alright, so this is NGC 6647. Doesn't give us a distance on this, but I know it has one.
We should look at this small Sagittarius star cloud while we're here.
Yeah, that's right there, and measure 11.
I remember there's some nice dark nebulosity in it.
Yeah, there is. All right. Okay, there we go. All right, so this is NGC 6647.
Sam S. wonders if you can zoom in some.
Absolutely, Sam. I will in a moment. All right, let me just do this. Let me finish typing this in. And then we will save it. And then save it exactly as seen. And now let's drop this down and zoom in. That's very pretty. Interesting. There are some stars that might be in the cluster that are red. So that could mean that this cluster has stars that are already done fusing hydrogen into helium and have gone into their first red giant stage, maybe. And that means that they're now taking helium and potentially turning it into carbon in their cores. And once that happens, all right. Well, first of all, I'm rushing things because I went right past something called helium flash in the helium horizontal branch. Never mind. We'll talk about it at another time. But the bottom line is, when the star runs out of hydrogen, the core contracts, and that contraction pushes out a lot of more intensity of radiation that pushes the star up into the red giant phase. All right, and then that helium is in the core, and that helium then can suddenly flash and start to fuse into carbon. And when it does that, the star has a new lease on life, and it begins to fuse this helium into carbon. It puts out a lot more energy, and then the star begins to get bluer. It starts to get hotter. As it does that, it seems to drift back toward the O end of the scale, but never gets to it. Okay, so it drifts back maybe from the M that it was to maybe a G type of color, and then finally, when the helium runs out, it contracts again, and now those outer layers get pushed off even more. And when they do, the star goes into the supergiant phase if it's massive enough, and that's called the asymptotic giant branch, and it goes up and becomes a red giant all over again. Now from there, most of the stars that go up the AGB branch like that will go supernova and end up exploding. And there are, of course, different ways that the behavior can occur. But isn't this beautiful? Okay, we're going to say this one more time with 18 exposures. Yep. New camera is doing what I think it should be doing. We're also going to go to a bright star and do a long exposure because we want to try something else. Daryl knows what it is.
I do?
You do.
Okay.
We want to see if we're going to get those halos.
Right.
See? He did know. Okay.
D, that depends on how big the star is in the first place.
Well, what was the question?
How long does it take for stars to go through these phases?
Oh yeah, that is a good question. Well, for a star like the Sun, we have a total life expectancy with our Sun about 10 billion years, but the time between the different phases of a star's life vary, as Daryl says, by the mass of the star. You know, how much stuff it has, and but you can go to a red giant phase in as little as 10,000 years, depending on what you are for a star and how the fuel is consumed. And some stars can do that for 100,000 years. So there's a whole different set of timings for the different types of stars. No one ever said astronomy was easy and simple, I guess. But it's pretty cool. Okay. Now while we're here, we're going to go check out the small Sagittarius star cloud. It's right nearby. You'll notice much greater increase in the number of stars. Let's first set us back down to 25%. And you'll also notice something else. You notice there's like this dark thing here, right? We see more over here. What is that? Is that a void, absence of stars? Or is it like what we've talked about before? It's not a void. It's actually dark material between us and the stars. And you will see that it's actually this dark material. Just a second. Sam S. says, astronomy wouldn't be half as much fun if it was easy. It's true. It's very challenging keeping on top of stellar evolution, the way stars work and so forth. Okay, we are guiding here, but it's looks like I was looking at the numbers. We'll give it a go. All right, we'll try this now. The small Sagittarius star cloud. Remember, we just looked at this open cluster called NGC 6647. And we'll clear this now. Dee Dee says it's difficult to comprehend, and it's hard to wrap our head around the fact that all this happened in the past, and it's taken this long for us to see the light. Well, yeah, I mean, space is big, and it is so big, in fact, that much of the light you see in that vast time machine that is the universe is light that left that source region tens of thousands of years ago, in some cases a few tens of years ago. The sunlight is 8 minutes old when you see it. If the sun went out right now, bam, we would be blissfully unaware of it for 8 minutes, because the light train is still coming to us before the end followed in. So it's pretty cool.
There's some of those nice dark clouds I mentioned.
Yep. Remember I talked about these voids, guys? I said, what do you think those are? Well, those are those dark clouds that Daryl mentioned. And then we have another open cluster right here. Wow, this is something.
An astronomer named Barnard figured out what the dark clouds are. People used to think they were voids in space, and he proved that they're dark nebulosity. They're dark clouds of material.
And he also did a catalog called Barnard's Catalog of these dark nebulae in the sky. So they're all labeled with B numbers for Barnard. If we go in here and we just center this up and zoom in a little bit, and then we go and we look at our deep space objects and we say B for Barnard. Okay, and we'll do sharpless while we're at it. Okay, then you'll notice in here that we have one here. This is the Black Hole Nebula, it's called. Okay, that's the thing that we're looking at on the right.
It's Barnard 92.
And so I was going to say, and you see up here, it's Barnard 92. It's also Lin's Dark Nebula 323. Yes, there's overlap. Yes, there's more than one catalog. And Barnard 93 is this dark object up here. That is Barnard 93 and Barnard 92. There you go. Pretty cool. And let's color correct here again.
That has a very three-dimensional look to it. It's just starting to come out.
It is, and it's going to get even better. In fact, if I go do this, we might actually be able to pull that 3D image. It is just an effect, so we don't really know from looking at it like this in 2 dimensions how it is really placed in the sky. It could be very close to that star cloud. It could be way, way far in front of it. One of my astronomy professors at one time, actually I went back, gosh, a few years ago, not too long ago. He was one of my old professors. I walked in, say hi to him, said, "Hey, Bill, how you doing?" And he goes, "Hey, I gotta show you a really cool photograph of the Milky Way I took." "Oh, let me see it." He brings it up, and it kind of looked like this. I was like, "Wow, that's interesting. Except it's not quite right. The stars don't really resolve to stars." He's got this little wry smile he's leaving on his face, and I realized, oh, I know what this is. I said, "Did you take a picture of a wet driveway?" He goes, "I did." It was a picture of his wet driveway. And then he says, "Well, you study UFOs, right?" I go, "Yeah." He goes, "Want to see a picture of a UFO?" "Yeah." So he actually shows a picture of the blue sky. And sure enough, there's this real interesting object flying through it. And I looked at it for a minute, and I noticed some weird distortions in the image. And I said, "You took a picture in the hood of your car, didn't you?" And he goes, "I did." He says, "I can't fool you." I go, "Well, I've just been doing it for a long time, Bill." But it's hilarious. I took a little drink of water there. Look at these strings of stars right here. Look at that. Those really pretty strings of stars right here. Okay. They're just beautiful.
Great big ones over on the lower left.
Yeah.
The whole lower left quadrant of the picture has long star trains in them, and then the dark trains also.
Yeah. And those might be defined by dust. That's not really quite visible here, but might be defining those lines of star trains. In part. Boy, this is interesting. Look at that. It's starting to really show some detail here. Let me see if I can pull some detail out in the clouds themselves. Just pull that over to the right a little. That's neat. Okay, so this is the Sagittarius SGR. Let me put small up there. Small SGR star cloud. Okay. Let's see what this looks like. That's interesting, Daryl.
What's that?
The image.
Oh, the whole thing?
Yeah.
Oh, I remember the dark nebulas from before.
Yeah. We have Barnard 92 and 93 here. There's another one out here, by the way, but
Yeah.
we're not capturing that right now. They're all throughout here. Barnard had a field day in this region.
Oh, yeah.
We're going to do one more photo, one more exposure to make it go to 15. And then we'll stop it here. Remember, we're doing this with a just past first quarter moon, so it's quite bright out there. All right, so we'll save it here. Save it exactly as seen. That'll be up there as small Sagittarius star cloud. All right, let's go check out more. All right. None of these things would be available to you by looking through a telescope, unless it was a very, very big telescope. You need to take photographs. Okay. Well, you know, gotta see the pillars of creation. Don't you think?
Well, you're very close to it.
Yeah. Here they are. All right. All right. Hubble took a beautiful photo of the Pillars of Creation years ago, and it's only been surpassed by the James Webb Space Telescope's photo of the pillars. And when they took it with the mid-infrared instrument, you could see the dark dust, and it was just stupendous. It left the Hubble image in the dust, no pun intended, because it showed the dust. Really something. All right. Now, when you look at it through a telescope, it kind of looks like this. All right, you kind of see this. Now, obviously not green. Okay, that's just my low light approach here so we can see it. But the pillars are right here. So let's wait for our guide star. We're locking in now. And we're going to do a 25-second shot. We don't need much more. This is pretty bright. But we got some wind, minus 3.7. Okay, so what we'll do now, actually, is we're going to go and do our refocusing again.
Mark, will you excuse me, please?
Sure thing.
Be right back.
I'll be right here. Alright guys, so what we're going to do is we're going to defocus our star images one more time. And wow, that's weird. The only thing I can say might have happened there is that something flew through that was bright. Could have been an airplane. Okay, so now we're going to scan inward and do our high-end focusing routine again. Okay. Okay, I'm waiting for this to start. Why is it not starting? Alright, let me jump out of that and go back in. Don't know what happened. Oh, I know what happened. That was stupid. Okay. It's at 25 seconds. I meant to do 1 second. My apologies. Sorry, guys. I made a boo-boo. Okay. Alright, so now... let's jump out of here again. Let's take it out of focus so we can get our optimal focus back. I wonder why it was taking so long. It's like, hey, what's going on? And then I realized. Okay. There we go. So now we come in and we scan inward. Here we are. And we'll get our beautiful view. I'm really looking forward to this. This is going to be a good one. I told you we're going to end up redoing everything because it's twice the resolution. Sam S says, can I get the pillars on a pillowcase? Absolutely. Okay. Well, okay. the Booty's void is actually it is a void, but why does anyone want to see nothing? You know, if we had a very wide field shot and we had a very, very dark sky that could support it, we could show a relative void in both these. But we don't. And we have a very dark sky out there, but we don't have a wide enough field, even with the other camera, where it was 2 degrees, 4 full moons across and 3 full moons tall, right? Let me refocus now. There we go. So it's going to come across and then go right back to the best spot there in the middle. And you watch our stars go to gorgeous little pinpoints. And there they are. Look at the tiniest little points. Okay. All right, good. Now, let's do our 25-second shot. Okay. There we go. Yay. Hop in our live stack. And that was the last one. That's up there. Barnard 92 and 93 in the cluster. Yeah, so we'll clear it. And then we'll see the pillars of creation now. It doesn't look like much, right? Until you do this. And the moon is inducing this blue haze in here. Because in spite of the best filters you might have, you do end up with a little bit of a haze from the moon. And we are close to the moon right now. So that's part of the problem. But the fact that we can do this at all with the moon out is really something. So there's the pillars of creation right in the middle there. Okay, we can zoom in a little bit. Okay, and what I'll do is make this adjustment to kind of just knock out some of the noise so you can see it better. There's the main pillar. Okay, and the secondary and the tertiary. And you see these little tiny globules here. Those globules, and then this is also a feature that we've seen before, but it won't be seen with this much detail. Beautiful pillars of creation. Again, hot young cluster right here. This hot young cluster is evaporating a lot of the dust and pushing it away. And the stuff that's densest at the leading edge of these pillars sets the characteristics for what's to follow, because if it's hard to push it away and make it evaporate because it's self-gravitationally contracting, then it's going to be on the lee side, on the back side, there's going to be protected stalk of material. And that's just what we're seeing here. These protected stalks of material caused by the the inability rather for the starlight to evaporate and push this dust away. It can push the gas away, but you can see it's still glowing red in here. But again, it's young. It has only been here for a few million, maybe 10, 15 million years. I'm not sure how old this cluster is. But that's what happens in these regions. Stalks and pillars like this are very common. We've seen them in other nebulae. And they're all made for the same reason. The same process is involved usually in making these. But there they are, the pillars. Look at this beautiful little subtlety. And this is the fairy. Was that the Daryl?
Yes, fairy. Sometimes the dark fairy, they call it.
Yeah, yeah.
It's facing down right now. It kind of reminds me of what is it? I guess an Academy Award or a hood ornament, something like that.
Oh, okay.
Its foot is to the left. It's facing down right now. Folks, can you see the eagle in the image? The eagle is actually pretty easily visible in a decent-sized telescope. The eagle is part of the pillars.
Is this the
That's
beak?
the wing.
Oh,
The
that's
eagle's head right there at the top right.
this here.
That part right there, yeah. That's the tip of the eagle's beak right there. That's
Okay,
his body.
And then this is
And
the
then
wing.
the thing to the lower right is his foot.
This is the foot.
Yes.
Or is this the foot?
The thing higher up.
That thing.
That's the foot right there.
Okay. If a child drew the eagle the way they see an eagle, this is what it would look like, yes. Pretty. Very nice. Let's pull a little more detail out if we can. We park these in a place where we might see a little more detail. Look at that. That's really nice. It's performing well, Daryl.
Uh-huh.
Let's see what happens if we move it way down. Yeah, very subtle glow in there. But look at now, you can see there's like a little, I'm going to zoom in. Okay. Look at this dark globule. Okay, it's got a reddish glow around it, so there's some hydrogen gas associated with this. This might be what we call a Bok globule. Okay, Bart Bok, an astronomer, discovered these globules were self-contracting areas, gravitationally condensing areas of dust and gas that could possibly spawn stars. And now we know that it could spawn stars and planets. That's really pretty. Holy cow. And this is much closer than we could get in the past. You know, and we're only at 91%. Wow. Lots of detail, man. Look at that.
It's very nice.
It is. Let's turn up the sharpening just to get a little better look. Now you can see the convolutions in this. You see the little spires sticking off, the stalks that are sticking off up there? There's some little ones sticking off there. Those are really there. There's actually two of them. And you can see a bunch of small ones in here. Wow. Really nice. Yep. I'm going to not know when to quit when it comes to this camera, let me tell you. Yes, sirree.
Can you zoom in on the fairy for a little bit?
Yeah. Let's go back to our previous and do this. So there's the pillar right there, the main pillar. Here's the fairy. Dark nebula in here. This is all dark dust mixed with hydrogen gas. So the hydrogen is ionized in here, which causes this glow. Again, these young stars causing that. Wow. So this is the Eagle Nebula. Right here. It's extensive. It goes way outside the field of view that we have here. So let's actually, let me pull these out of the way. Okay, and let's drop this out of the way so you can see it. See it growing.
That's nice.
Here. It is.
Yeah. See below that dark globule you mentioned, there's looks like a red one just below it. Kind of a red spot below the dark spot.
Really? You're saying this one?
Yeah,
Oh, right
that's the
here.
dark spot. Yeah, and then the red
Yeah,
spot right there.
yeah, you're right. That is true. Yeah, we're catching a lot, and this looks 3D, obviously, right here. It looks like a 3D object. And in all likelihood, it is a 3D object, because this is an object that's a dark mass of dust with some hydrogen gas also condensing with it. Then we've got this one down here, which is mostly hydrogen gas that's gravitationally condensing. That could become a star at some point, possibly. This could become a star, and might have some planets, lifeless probably at first, but it could happen, and that's really neat. There's our fairy right here, okay, and our pillars, and that little spire I was talking about was this guy right there. You see that little spire sticking up? That's really important to see those little spires. They kind of remind me of the Andorian in Star Trek. The antennas on their heads. Wow. Let's see if we can pull a little more detail out of this. A little more detail, and add some contrast a little bit. And I'll move this in a little more. Okay, and then let's zoom out. So you can see the full extent of the region here, guys. This is just a immense region of gas and dust. And it just happens that this star cluster, because it's so bright, is causing a lot of the hydrogen in here to ionize, and it's mixed with that dark dust. So when we look in here, one of the things that is important is we see how the dust itself is shaping these pillars. The gas is mixed throughout, and the gas is being pushed back by the stellar winds, and the dust is persistent. It's thicker, it's heavier, so it doesn't go as easily. But at the front end where it's denser, it stays put, and so it forms these little pillars behind it, so the stellar winds can't push anything behind this lump here. So that's really cool. Look at that. Just beautiful.
That's very nice.
Okay. Yeah, we've done 27 frames on this. So I think what we'll do is we'll stop it there. We'll actually let it go to 28 frames. Let's pull the telescope back into the view here. There we go. And move this over. So what do you think of that, guys, huh? So a new camera a success or what? This is live. It's happening right now. You're seeing this live in real time. I'm just, I don't know, Daryl. I mean, I haven't seen anything ever approaching this with our previous camera.
Yeah.
Okay. Well, there's 29 frames. Well, if I waited 29, I'll just wait for 30. Izabela will be happy that I waited for 30, because then it's that much less noise in there. And the guiding is okay right now. I mean, it's a little bit off, but it's not bad. Look at the subtlety in the dark fairy. That's really pretty. Okay. Saving the Eagle Nebula. Saving exactly as seen. And what is exactly as seen? I'll show you. This is the image that's being saved right now. That's what's being saved right now. And so what we can do is we zoom in on that. Okay, this is what you're going to see up there. All right, that's the raw file. But we'll be able to, we're going to be able to take that and just do wonders with it, as you'll see. Let's get out of here. All right. Okay. So we'll get out of this. All right. That's just something else. Wow. All right. Okay. Let's go to our stars, our charts, and see where we're going to go next. See where the moon is? It's so close. You know what I want to try? Now that we can, I want to try this guy. Okay, this. Well, first things first. I'm gonna go. I'm gonna go to Sadr. I'm gonna go there only because I want to make sure our alignment's good, because you can't see this object unless you're aligned. And once we know we're aligned, I can position it invisibly. So Sadr should be showing up here momentarily. You won't be able to miss it.
Is this for your bright star test?
Yes. So there's Sadr right there. And we know that when we look at Sadr, we see rings. I can see rings around it now.
Yes.
But let's see how bad it is.
Faintly.
Huh?
Faintly. Fainter than before.
Yeah, actually, that's true. Well, we're gonna see. Okay, we're gonna bring Sadr in here. We're gonna go south of the telescope to bring it up into the field more. All right, and I'm gonna kill two birds with one stone. I'm gonna go here. I'm gonna go to the west. No, yes, a little bit to the west again, and head north a bit. You see where the telescope's pointing, guys? It's pointing straight up, practically. Alright, so we get Sadr on our crosshairs here. And move it in. Alright, that's pretty good. Now let's see how far off it is. Alright, so we zoom in now. And it's not that bad, but we're going to fix it now. Our crosshair is going to go right on Sadr. There we are. Okay. Now we're going to do a exposure to see if we get a bright halo. We may still get halos, but we're going to do a 20-second shot. You'll also see nebulae around it, because this is where the Gamma Cygni Nebula is as well. And it would be very tempting to want to do that because it's gorgeous. But I want to get this other thing because it's a much more interesting object. Okay. Alright. Let's see. There's our Eagle Nebula. That's beautiful. Okay, we'll clear it. And prepare for Sadr. Let's see how bad the halos are. Okay, we're still getting halos.
Yeah, that's a pretty bright star, though.
It is. All right. And you can see the Gamma Cygni Nebula out there. Yeah. Okay. Well, that was our test. So now what we're going to do is go to the other object I'd like to see. And now that I know that we are well aligned for where we are, I'm going to move us there now. All right. This is where we're going. And there's a reason we're going to this, because it's a very interesting location for a number of reasons. And you'll see why. So, off we go. I had that problem before. It didn't want to go here. So let's try this.
What are you trying to do?
I tried to go to that little star, and for some reason it didn't want to go. It was really strange. But what we want to see is right in the middle here now. But I got it to go there. Alright, so we're looking for our guide star now, and it's going to have no trouble finding one. But while we're waiting, we're just going to set up our shot here of 30 seconds. We're actually going to photograph a subtle nebula that's two colors. It's going to be red, and you're going to see a green nebula with it. And there's a reason why we're going to see that. So, let's check this out now. Okay, we know we got that. We're not going to see that, but that allowed us to get our answer to our question. All right. Okay, subtle as it is, you'll see it get better.
I see the green.
Yep. And let's bring it out better, and let's color correct. Color correction will show it better in there. It already does. Alright, this is just one exposure. Here comes the second one. You'll see it gets more defined. Yeah. Alright, let's do this. Okay. So what's going on right here is this is a red cloud of hydrogen gas in here, but then you have this arc of green. We're looking at a Wolf-Rayet star, a star that has shed its outer layers. And then, in fact, this particular Wolf-Rayet star is called WR134, and it's a interesting location, and interesting because it's near another one, which we'll see, and amazing because this green is difficult to discern even amongst the rest of the stars in the area. It's almost invisible. So you gotta really play with the settings just to get it to come out right.
Is this the Wolf-Rayet star that Izabela processed a few days ago?
Yes, it is.
Oh, she really pulled a lot out of this image.
Yeah. So we've done 120 seconds on it now. We've done 4 30-second exposures. Hey, Donald Kunzer, how are you? Yeah. And what we do first when we process is we remove all the stars. And we leave only the subtle nebula. And then we work on processing the nebula, and then we have a layer that's just stars and a layer that's nebula. Very important to do it that way.
I remember this now. The Wolf-Rayet star is the brighter of those two white stars to the lower left of the green arc.
I think this is the star that's the Wolf-Rayet. It's the bluer of the two. It's a very, very hot star. And this star is too red.
You just have to make a monkey out of me, don't you?
Well, I'm just saying what I observe.
I'm just going by what I read the other night. So it was the one slightly farther away.
Oh, well, go correct me then, because if it's, I just think that it makes more sense that it's a hot star, and an orange star doesn't fit the bill for a Wolf-Rayet star.
What's the number of the Wolf-Rayet star again?
WR134. The Wolf-Rayet is, we're looking at the hot core, so I'm expecting we're going to see that right there. I think that's, I don't know if, I would not expect this to be the star. That arc is really pretty, though.
The image on Wiki says the brightest white star just below center. And in this image, I mean, it's rotated like 90 degrees or more from your orientation, but the one they're talking about is the one that's matching your orientation to be to the lower left of the two in the pair.
They're trying to say that's the Wolf-Rayet star?
Yes.
Okay, well, see, now I'd have to go into Sinbad and see, because the nature of Wolf-Rayet stars is, as you know, they eject their outer layers because they're so hot. Their stellar winds are extremely strong. And it leaves the very, very hot central star, which is going to go supernova. So it's not going to be a red star because the red star would imply it's a supergiant. But these stars are just showing almost just their cores, which are not going to be red supergiants. So I'm not sure how that ties in, and if that's what it says in the wiki, that doesn't mean it's right, actually. I've found a lot of errors in Wikipedia astronomically. So, but hey, I don't know. I mean, like I said, from a point of view of the physics of a Wolf-Rayet star, I would wager money that this blue star is actually, this one right here, is actually the hot central star of the Wolf-Rayet complex right here. But, you know, interestingly, we'll just have to wait for that confirmation. But that's a beautiful blue arc. We're going to call this WR134. WR134 Wolf-Rayet star. I'll save it now, and then we'll save it again after doing another couple of shots.
Gladys, yes. Wolf-Rayets, they are, this one may actually be 400,000 times as bright as the sun. That number comes to mind for some reason. Generally, you might be talking 500,000 to 1 million times the brightness of the sun, and it's energetic star that it's putting out tons of radiation, and it's probably sterilizing the neighborhood around it.
Yeah, to more star systems too. And all these Wolf-Rayet stars are destined to be supernovae at some point. They're already in the final stage of their life when they've ejected, all this envelope of material out here. See, this stuff that's out here, this is all the former envelope, the stuff that made up the outer parts of the star, and then the I'm going to point to the star for just a point of view. And this star that's left in here, that's actually the exposed core of the star, which is extremely hot and blue. And so this green nebula here is the oxygen that's been expelled. Now, you would say, why oxygen? And it's because we've talked about this before. The red is the hydrogen from just the interstellar medium, but hydrogen is the most common element. The second most common element is helium, and the third most common element in the entire universe is oxygen, and followed by carbon. Now, hydrogen, helium, and oxygen have spectral signatures that you can readily see. Carbon, not as much. So basically, this situation is something we'd expect. Stars would be made of a lot of oxygen because that already was out there. Now, stars do fusion; they don't do combustion. So when we talk about a star that's fusing, and you'll hear it stated, well, a star burns hydrogen into helium. The word burn is the wrong word. It's fuse. It's called nucleosynthesis. Big word. All it means is it takes two hydrogen atoms, smashes them together under such pressure inside the cores of these big stars that eventually what they do is they actually combine and form a new atom, one that has, say, 2 protons in its nucleus instead of 1. So it goes from hydrogen to helium, the next element in the periodic table. So that's nucleosynthesis, and you can imagine it works its way up the table, gets to about iron, and after iron it can't go any further because it takes more energy to fuse iron than it gives off when the fusion takes place. So that's why when it does fuse heavier elements, it's in the form of a massive explosion where there's nothing else that's going to happen after it. So it's a last-ditch kaboom, immense pressures that will form some heavier elements in that. So that's pretty cool. I wish I could translate what our Russian friend said there in the chat. Wolf-Rayets are like Costco-sized sanitizers. That's hilarious. You see Gladys said that?
Yes.
All right, we're at 21. This is pretty good, and it's nicely focused. The last one was not that we did, and it was just because I wanted to see it. Okay, we'll say this exactly as seen. And now... yeah?
A suggestion or request?
Yeah.
When you're done here, and you go back to Stellarium, can we take a look at something real quick?
Sure. Let me set us into our night vision mode here, and once we do that, okay. Now we'll go back to Stellarium.
Cygnus star cloud. Have we ever looked at that?
Isn't that the Tulip Nebula?
I don't know.
Let's find out. Yeah.
Okay, yes it is.
Yeah.
All right.
Yeah, we've looked
I
at
just
it.
didn't see it by the name Tulip Nebula.
Okay.
Bonnie's here. Hello, Bonnie.
Bonnie, Anahata 77. Nice to see you. Okay, now, that was an example of a Wolf-Rayet star nebula that we just saw. This next one is also a Wolf-Rayet star nebula that you're going to see, and it's a lot more pronounced. So you'll see that the stars, and it has sent off a number of other materials, and this one's dead center. It's perfectly placed. So this, as you see, is an example of a Wolf-Rayet star that's actually also in the final stages of its evolution and will be going supernova. This is the star right here that's we're talking about. Okay, and let's do this. Let's do a 30-second shot of this one as well. We are going.
Izabela's not here yet. She's usually up by now.
I know. I didn't see her.
Yeah, be 7:30 in the morning there.
Yeah. All right. So let's go into our live stack here. This is a second type of Wolf-Rayet star. Okay, we're going to get out of this. And we'll name this the Crescent Nebula. There it is. So the Crescent is a very obvious nebula. And you'll notice something right away, and that is that it doesn't seem to be symmetrical. Like the other one, it seems to have an arc in it. And the arc is here. And the other one had this greenish arc. What's with the arcs, and why don't we see spherical stuff? Well, we do. It just depends on the density of the local interstellar medium where this is happening in all likelihood. And the stars could be rapidly rotating and expelling stuff along their equators. This might be equatorial expulsion this way. And this is actually kind of an elliptical shape. You'll see it as we develop more imagery here. Okay, if I do this, and once it pops in, all right, there you go. So you can see a little bit more. All right, and it'll get better as we go. But we only got 3 exposures stacked here. But you can see that Wolf-Rayet stars have a different kind of outflow. When we look at Thor's helmet later on in the season, you're going to see something radically different from either this or the other one we just saw. So when I say the local interstellar medium, you'll say, well, wait, if this is the star, how come it's not symmetrically around the star? Because the star is blowing this stuff off, but you've got to remember that all throughout here is stellar winds from other stars pushing in all directions. And if this stuff is moving out from the star, it's moving out at a certain rate of speed, and that speed is dependent on what's in front of it. So right now, we're seeing this buildup along this front here, which could be the result of like a snowplow effect, where this stuff is plowing into dark dust and other gas in the interstellar medium, ionizing it and causing it to glow on its own like this. All right, which can explain the different colors we see here and here. This could have come from the star, or it could just be ionized outflow in the interstellar medium caused by the Wolf-Rayet star. There's a lot of possibilities here. And I think they know a lot about this particular nebula. Let me color correct. And then let's put it where it wants to go. So there, you can see this a little better now. You can see the filamentary structure in here that we've never been able to have access to before. And we're going to just move this over a little more. This black level is what we set. And you see that white curve? That's the average of the red, green, and blue curves. So if we move it to the very top of the curve, okay, then it's as dark as you really want to allow it to get without losing a lot of detail. Go beyond that, and now you're on the other side of the curve, and you're going to be depriving the image of seeing a lot of data. That's why it looks like that. So we typically go just to the left of the curve. So we get the most bang for the buck and the most data. Well, look at how much data is in here now. This is really cool, Daryl. And we can
interesting little wisp of green
right here.
Yes.
Yeah. We've seen that before, but we've never seen it with this detail. It actually has some different tendrils associated with it.
Yeah.
Okay. Very nice. Wow. Ronald is here. ERRT Radio. ERRT Radio is a wonderful channel on Mixlr run by our friend Ronald, who is here in the chat tonight. Welcome, Ronald. Okay. We've done 10 here of this. And by the way, our gain, okay, the gain is one of the most important elements, okay, to this. It's the sensitivity of the sensor, okay, and then the exposure time is how long we allow light to fall on that now sensitive sensor. And you'll notice down here it says it has a temperature of minus 15 degrees Celsius. That's the current temperature that we have the sensor running at. So the temperature in the building is 25.38 Celsius right now. And we have cooled the sensor down to negative 15 Celsius. And we did that because we wanted to lower the noise that you associate with, or you can associate with these sensors. And that's what we're seeing here. We're seeing all this beautiful detail courtesy of the fact that the sensor is running so much colder than the ambient air. And it's all sealed up, so that cold doesn't cause frost or anything to occur because it's actually sealed from the outside air, airtight. And we even have these desiccant tablets that suck up any moisture inside the camera. Ronald says the results with the new camera are amazing. Yeah, it is. It's just been great. Ronald, if you've been watching the whole time, you saw some crazy details. We're not gonna do, I don't think, the veil tonight, Daryl.
Okay.
I do want to go and look at a piece of the North America Nebula. Ronald says, are those bright stars at the top of the cloud the same distance? These he's talking about. I don't know the distance to these stars offhand, Ronald. This looks like it's more than one over here. Okay, this one might be a singular star or binary. But you notice, by the way, guys, notice this. Look at the green. See this green? All right. So this Wolf-Rayet star has also expelled a lot of the oxygen envelope around it. And as I said, I'm not sure whether this red material isn't just ionized hydrogen in the region that's part of another cloud. You'd have to analyze the velocity that it's moving versus the velocity this is moving. So this might be the only stuff here, the green, that's associated with this Wolf-Rayet star. This red at the end might be just the impact effect of the shock wave from this material heading out into the interstellar medium. But I don't know that for sure. I actually think that is a somewhat likely scenario. Renee. So yeah. Okay, so we'll go to 18 exposures on this. And let's see if we can drop this down to make the noise a little more subtle. See, when we drop it that much, it kind of removes some of the other details. So we want to leave it up higher so we can brighten a lot of the stuff in here. And any of the grain in there, that noise, we remove that. We get rid of it very easily. Okay. Crescent Nebula, save. Crescent Nebula, save exactly as seen. Okay. So that'll be available again, skytourlive.org. You go scroll down and you can pop over and see this exact photo and download it and enjoy it. Everything is free. If you want to buy stuff, you can buy stuff. Go to the Etsy store, the Sky Tour shop on Etsy, or go here and order some professionally made prints of some of these things that we actually spend a lot of time to process. So there's no grain, no fuzziness at all. Okay. All right. Okay, we're gonna head up here. Okay. And we're gonna do something now. All right, this is gonna be upside down to us. If we zoom in, you'll see the letters and the, well, you can't see because it's red. The letters are red. All right, let's go. Let's go here. We're gonna go right here, and we're gonna hope that it pulls us in right there. Okay. All right. We're just gonna tell it to go to that spot in the sky. Okay. And you're gonna see our crosshairs are gonna show up right in here. Here they come. Boom. Okay. So now what we're gonna see is upside down. Because you see how the letters, and now you can see you gotta turn your head upside down to see it the way we're gonna see it in here. So that's all. Okay. Let's zoom out to our 25%. Okay, so there we go. So it doesn't look like much right now, but let's first of all get our Starlock system running, and I'm going to just do a 20-second exposure to make sure that we have it centered up nicely. And we'll leave this up right now. Hey, Bullwinkle. Alright, let's see what we've got. I think it's here. It seems like this is where it is. Let's see. Yeah. Very interesting. Alright. So what we're going to do is I'm going to go back to 1 second here for just a sec. And I'm going to drop this down. In other words, I'm going to head north with the telescope. Because I want to frame something really nicely here. Okay, one more little push. Okay. Alright, that should be good. Alright, we'll wait for our guide star and then we'll come back in and do it again. This time we're going to go 30 seconds. And we're underway. Guiding is nominal, actually looking very good actually. This should be a good shot. Okay. In here now, we'll see a last look at the crescent, which is in our image buffer. Look at that. Incredible, huh? Wow. The power the universe has, man, let me tell you. It's crazy. Okay, we're going to clear this now. We've saved it. And the next image you see will be the North American Nebula, or a section of the North American Nebula. And that section is right here. This is called the wall. Right? Actually, it's still a little out of the way. I gotta bring it down a little more, sorry. Gosh, it's gonna be really pretty though. Okay, so let's drop it down a little more. I thought it was very interesting, Daryl, when we looked at this the other night, and we just we noticed that thing that was sticking up over here was actually something that has a lot more detail to it to its left. It was actually a dragged out wispy object.
You mean the part that I always make fun of?
Yeah. Yeah, it's actually a dragged out wispy object. Alright, let's see here. Okay, we're going to do this again, 30 seconds. And I think we are where we need to be, so I'm going to just go for it. Jump into a stack. Start building an image for all of you. Yeah, this is going to be down here now. And just wait. Just wait. Oh, man. This is crazy. And this, remember now, we're just past first quarter moon, so you know more than half the moon's illuminated from our perspective. You know, if we want to talk about it that way. So it's on its way to waxing gibbous in the next couple days. Oh yeah, perfect. Look at that. Wow. Yeah. So we're gonna move this over. We're gonna color correct first. There we are. And we're going to drop out a little of the blue. Okay, and this will peek back here. So you're going to see subtle detail over here now, to the left of this column. But look at all this black dust. This black dust is amazing because it really represents, like I said, where life originates in the universe, when it originates. It's within that blackness that life occurs. The devil's in the dark, you know what I mean? This is crazy. This is beautiful. Make this darker. Just at our peak. Alright, now let's pull down our mid-levels to kind of reduce the noise a little bit. Okay. And then pop this back a little. I had taken a picture of this the other night. I just couldn't stop. I mean, it was just I was amazed at how well this was performing, and I just had to keep going. RJP, how are you? Ray, what do you mean? I think something camera does with imaging. What does that mean? Wow, this is really pretty. Let's get rid of this for a little bit, and let's drop this out of the way for a while. Let's increase the size here of our image so we can see the North America Nebula. This is a section of the North American Nebula. This is the Gulf of Mexico right here. Florida's over there. This is Mexico in the North America Nebula. Yeah.
Check our chat, Mark.
Okay. The North America Nebula is got a lot of features in it, right? And in fact, the North America Nebula itself has this particular feature that we're looking at right here. Okay, this right here coming all the way down, okay, has a specific name, and that name is called the wall. And so that's why we have this label here for the wall right there. Okay. Let's see here. Okay, 1 second here. Oh, there we go. Okay. Might have missed that. Okay. Ray, you're asking whether there was a STLS tonight or just a Marc and Daryl dance? Well, that's a little bit rude. But it actually wasn't that way at all. I was actually still in Arizona, and I had literally gone out to the observatory, drove 2.5 hours out to the observatory through the desert, and collimated the telescope, and then drove 2.5 hours out of the desert back to Mesa, Arizona, and then from there, on one screen, I have several, I have a big, large curved screen here, but on one small screen out there, I actually started taking photographs to confirm what was going on. And when I did, I was only in Skype with Daryl and Izabela, and I was sharing with them the images that were coming in because they were phenomenal. I couldn't stream out there, so no. And it wasn't anything like what you say. So anyway, there we go. Look at that, guys. Look at that. Oh, that is just beautiful. I don't know, Daryl, that looks pretty good, doesn't it?
Sure.
You literally see all the stars in here, and this black dust, you'll notice there's no stars. This is because it's obscuring a lot of these faint stars behind it. These are all in front of the dust cloud, and when they get red like this, and they redden, it means that they're kind of immersed in it, and you're still seeing some of the starlight coming out. Here's a perfect example right in here. Let's zoom in. Okay. So right here, you have these beautiful red stars. Are they all red? Not necessarily. but they could be immersed in enough of this dust that we're seeing interstellar reddening, because just like the sun looking red on the horizon because it's going through more stuff in our atmosphere, particles, molecules, the blue light gets scattered like we saw. And that blue light getting scattered leaves only the reddish orange yellow light to get to your eye. And so that's why the sun looks red on the horizon, and that's why these stars look red inside these nebulae. If they look really bright white like this, these are stars on this side of the nebula. And the stars inside the nebula will show up as diminished red objects. Now, yes, some of them can be M-class stars, very red stars, low temperature. But in all likelihood, many of those stars are not that way. That is the most plentiful star in the universe, but it doesn't mean that these are all M stars. They could just be a lot more blue in color, bluey toward the blue end of the spectrum, than they show because we're seeing them through all this dust. This is a stunning image. And so we'll back out a little more to show the whole thing. Look at that.
The brightest part of the wall just below center as we see it now.
This?
Farther down, the brightest part,
right there.
right there.
Yeah,
That looks really cool.
it does. Let's see if we can zoom in on that. Yes, we can. You move it up a little bit. I didn't want to do that. Okay, I'm gonna move it up a little bit. Now let's do a subtle reduction in the noise here. Wow. It's like you're looking at, it almost looks like you're looking at a fireball in slow motion. You know? Look at the detail in these wisps of dark nebula here. Again, all shaped by the, in the cosmic tapestry by the stellar winds of the nearby stars and so forth. Just beautiful. Now we get to this part up here. You can see more brushed material here. It's just crazy. It's really pretty. And then up here, and I'm just gonna increase our brightness in this area so you can see it a little better. Okay, you can see this is not just a thing sticking up. It's actually got a bunch of subtle material to its left. Really something. So, backing out to show the entire image. There's the whole image right there. The Cygnus wall.
That's really something.
I hope you guys like that. Alright, and we're now going to save that. First things first, let's dock this back up. Okay. And we're going to move that up and move this up. Okay.
Mark, excuse me again for just a moment, please.
Sure, and I'm going to move the telescope back into view here. There we go. That's just something else. That's really pretty, guys. Daryl, thank you for putting up that address. Wow. All right, one more image. See the beauty of that spire? That's light years long. Can you imagine a cloud of ionized hydrogen light years in size? And there it is. Now, I wrote a program that will allow me to, if I can measure this, I can measure that length in what's called arc seconds or arc minutes, and I could convert that to an actual size in light years for this object, knowing the distance to it. Now, it takes going into Photoshop to do that, but it's really interesting. Okay, North American Nebula has been saved, and we're going to save it exactly as seen. Now I'm going to push it and bring out more detail. Okay, and I'm going to save it exactly as seen again. Okay, this does not alter the first file I saved, the FITS. The FITS file is the astronomical file format, and that isn't changed by what I'm doing here at all. Okay, that has a lot of subtle detail in it hidden. In fact, when you look at a FITS file, it just looks like you see the brighter stars, you don't see any of the clouds. You got to pull all that data out. I'm actually doing that here on the fly with you, for you, so you can see what this will look like when it's fully processed. So I can, for instance, get rid of most of the noise if I want to, and I can also take this image and pop it out even more like this. I want to show you something though. If I go here, right, this is what it looks like, and then we come over to this histogram over there, as you can see it, and if I pop that up, what it shows is everything that's here, all the detail that's in here. All right, so that's what it really looks like if you wanted to, and we can adjust that and play with that too. Bring it down or bring it up. So we can just adjust all of this, all these settings. Takes a little longer, but you can see the amazing amount of detail in this. Look at all that. Here's something that was out of reach for us, but last time was this. This looks like a hand sticking up, doesn't it? Let's pop that down. Wow, that's impressive. Most impressive. But you are not a Jedi yet. Okay, we'll save the FITS file again. Again, this is not representative of what changes in the FITS file. The FITS file is raw and leaves us to do all the processing. But these files, when I show you these are the guys you see that you can then download and check out. Okay, so now we'll save exactly as seen. All right. Incredible. All right. All right, let's go here. Check out at least one more. Let me do it this way. That's what I want. We're going to look at what's called the Bubble Nebula. The Bubble Nebula is a phenomenal location, interesting because it's also a Wolf-Rayet star location. And we're going to head there right now. All right, let's do this. Okay. Off we go into the bubble yonder. We can shut that off. There it is right there. Too bad Izabela isn't here. She won't get to see this. She'll have to see it on the replay. Okay. So we're going to go to the north to bring it down. We're raising our telescope up. Okay. And we're going to go to the west. Yes, there's a nice cluster up there. But there's a lot going on down here that we got to see. There's also another big nebula down below here, but we're going to focus only on the bubble tonight. And let's just do this. Okay. All right. Okay. So this star right here is a Wolf-Rayet star right there in the middle. And it's blown off its outer layers as well. And as you'll see, we just saw two other Wolf-Rayet stars. We saw WR134, and then we saw the Crescent Nebula, which is also another Wolf-Rayet star. And now we're going to look at a third Wolf-Rayet star, and you'll see how different yet the same they all are. So this one will do for 25 seconds. It's actually very bright. We don't need to go very long. All right. Is that you back, Daryl? Okay, maybe not. Okay.
Yes.
Oh, okay. Okay, there's our Cygnus wall. And now we're going to look at the Bubble Nebula. Okay, there's the bubble. All right. And the bubble, again, is, as I said, a Wolf-Rayet star. And what's interesting about it is that it has this beautiful, almost perfectly spherical envelope around it. Now, for the WR134 we just saw, and for the Crescent Nebula, you saw that they were compressed, they were squished on one side. This is not like that. In fact, you can see an almost complete bubble here. That's really, really impressive. All right, and let's do this and color correct. All right, and then pull this over to the peak. Remember how small the bubble was in the previous camera? It was just a tiny little thing in the previous camera. There's another nebula down below here, as I said, but we're not going to look at that one yet. I think that's the Lobster Claw Nebula. Do you remember that, Daryl?
Vaguely. Remember the cluster in the upper left here.
Yeah, we're going to have that in here. Hey, Prow, how you doing? Just noticed you're out there. Mike, good night. Hello, Marco. Yeah, Cosmic Ray, all the camera settings are included. We capture for each image, we capture like 10 different elements of the image. It's very intensive work because I haven't written a parser to take all the data and separate it in the text files, and that's another thing to do. That's an easier thing to do, is to just parse all the data and then insert it into the database in the right fields. But it'll take some time. I haven't gotten to that yet. Look at this beautiful nebula, Daryl. Look at that.
Mm-hmm.
All right, now we got some time to zoom in. Wow.
You say this is also a Wolf-Rayet?
Yeah. Yes, it is. I think that the Wolf-Rayet star is actually this one right here. Right there. At one point I thought it was this star. You know, but because that looks like the one you would expect. But again, we're thinking symmetry here. But I'm thinking that's the star, and I think I checked it on Sinbad, and that is the star, which was odd to me. But to your point before about the other star, these two stars do look like they're a little bit orange. So it could
I
be
looked up 5 or 6 different sources on that other star, and it was that other star.
So was the orange one?
Yes.
Okay. Okay, well done. I do not mind being corrected as long as it's intellectually accomplished, and you did it. I'll have to investigate the Wolf-Rayet phenomena then to see a little more, because this one is orange as well. Look at that. Holy cow. Look at this in here, Daryl. Never saw that before. Look at all those little convolutions.
Oh,
yeah. This is one sterilized local environment around that Wolf-Rayet.
And all that was blown out by the Wolf-Rayet, correct?
I'm not sure about this. I think this is what was blown out. I don't know if this was also blown out. This may, again, be that ionized gas that's just local to it. Like this stuff here is like probably ionized gas with dark nebula, because the dark nebula wasn't blown out by it. So this is just in the region, and this started doing this Wolf-Rayeting thing at this location. I mean, look at this.
The area immediately to the right of that bright star.
Yeah.
That right there. I mean, that looks really, really bright and hot.
It does, and I'm not sure.
It's all red. That just kind of screams that it's being heated by that star next to it.
It sure does look it. Let me zoom in even more. Okay, this whole region is an area that's been superheated by this star. But because the interstellar medium is different densities in different places, you see a perfect bubble here, but this star isn't centered in that bubble.
I understand.
So that always... I try to figure out what would make a perfect bubble occur. Now, here's a possibility. That could have blown off when the star was in here. And then the star has been moving over the course of thousands of years. And possibly, if that's the case, we have to get the what's called the proper motion of this star. If it's moving, I would expect it's moving from where it might have come out symmetrically to here over the time that this happened, so that could give us a rough idea of when this happened.
I wonder if that's like a bow shock.
Yeah, but if you look at it, it's a complete circle down here.
I understand.
So that's interesting that does that. Here, watch. Let's pull this in. So now you can see the other side of it here a little bit. Wow. It sure looks like a bow shock, doesn't it? That is crazy. But these Wolf-Rayet stars are actually not well understood. And as Daryl's mentioned before, and I've mentioned a few times as well, these stars may be the stars that we sometimes see in the center of planetary nebulae. But that's just a theory. It hasn't been proven. They share similar characteristics.
Star cluster we saw to the upper left is Messier 52.
Okay, let's go check that out. That's up here, right here. Oh, that's cool. Look at that. It's like a little jewel box.
That's an open cluster for you.
Yeah, absolutely. Look at that. Wow. This is just beautiful. Let's really push this. Okay, now you can see a little bit more of the interstellar medium around this location. And let's pop this all up. And you can see all the red nebula all throughout this region here that actually exists in there. And when we do the final processing, you'll be able to see all that. Look at this. This is beautiful. Izabela should have waited for us to do this one, because she got one of our images for the wall at her house. Look at that. Look at that. Wow. Zoom time. Look at these, like these little like stalagmites. They're sticking off the top of the, and they're probably dense areas that are not being eroded as efficiently as the stuff around it. Wow.
The bright star is energizing the nebula. It's an O star, O6.5, 37,500 K.
Mm-hmm.
Says nothing about it being a Wolf-Rayet star.
Okay.
The exact classification of this star is uncertain, with a number of spectral peculiarities and inconsistencies between the appearance of the star and the effects on the nearby nebulosity, but it is undoubtedly a highly luminous, hot, massive star.
Okay. I have no doubt, though, that this is a Wolf-Rayet star. It's just I saw that in many places about the Bubble Nebula. So, and looking on Sinbad, you can identify this star as the Wolf-Rayet star as well. So I'm not sure where what that is.
Izabela's here.
Hey, there she is. This is your favorite nebula, Izabela. Look at this with the new camera. What do you think? Isn't that incredible? Well, one of your favorites. Oh, that's okay. He says she didn't get the notification. That's okay.
I bet she's been here the whole time. She's been lurking.
Maybe so. Prow asks how large or wide the bubble is. Again, we get the distance. I can figure that out. The Bubble Nebula also has a definitive diameter that can be found as well, probably online. It's probably been figured out a long time ago.
Give me just a second.
All right. Well, we're gonna save it at 30 here. Okay.
It is 3.5 light years radius.
Okay. So kind of about the size of a planetary nebula in general. Planetary nebulae can be 2 to 3 light years across. Very cool. That's stunning. That is really stunning. Do it one more time here. There we go. All right. All right. All right. Okay. Now, one more object. Can you guess which one it's going to be?
Elephant's trunk.
Nope. No. How about Measure 33?
Oh, sure.
All right. There's so many cool things coming up now. Well, we also have the Cave Nebula. Oh. Okay, no, we'll do Measure 33. We'll do Measure 33. All right. And
looking at an image of the bubble and the bright star, BD plus 60, 25, 22. A close-up on the bubble and that star's location in the bubble. It's very complex in there, and there's a whole lot going on that we're barely touching the surface of, so to speak.
Yeah.
Anyway.
Cool. Well, thank you for that. Okay, here's Measure 33. When you go to higher latitudes and you tell the telescope to move, it moves more through more sky than you expect. All right.
I've been posting all night, Izabela, since you weren't here. She got on me the other night she wasn't here and I forgot to post. So I've been very assiduously posting links to the server tonight. You're welcome.
I only saw the last couple that you did. I didn't realize you've been doing them all night, and thank you.
No worries.
All right, 30 seconds on this guy. We're guiding already. And let's go for it. This will be Measure 33 round. Oh, look at the bubble. Look at how beautiful that is. Holy cow. Wow. Well, okay. Measure 33 around 2.7 million light years away. So if you're having trouble wrapping your head around how the light you're seeing left there 2.7 million years ago, you're not alone. And here it is. Beautiful galaxy. Let's how you doing energy-wise, Daryl?
Energy-wise?
Yeah, you know.
I feel the pumpkin coming on.
So do
somewhat.
So do I. This will probably be our last object, but look at this beautiful spiral galaxy, guys. See the arms here? Okay. And this is a loosely wound spiral, so it's classified as a SC. SC. So capital S for spiral and then little c. There's a little more complexity there. It's probably an SAC, but let's go look at it. It's a beautiful galaxy. All right. And you'll notice that there's lots of identified objects inside. And you'll hear Daryl talk about NGC 604 a lot.
Me?
Which is, yeah, you talk about 604. Is that the largest H2 region in the galaxy?
It is.
Yeah, and that in this image, it's right here.
Yep. Now, when you showed us this the other night, it was a direct view on your monitor, and it was really red. And it seems to have lost a lot of that red punch now.
Well, let's see. I just did a color correction, and now it looks more red now. Yes, the H2 regions.
Okay.
But you're right. I think it had more red the other night.
Maybe when you get a few more images stacked. I know we were seeing, actually saw detail in 604 also.
Oh yeah, it's there. If I zoom in, you can see it even now.
You can see some, what you'd call it, convolutions or whatever.
Yeah, there's some complexity. We stack more, you'll see. It's only got 6 stacked right now. But it'll really show very nicely with a few more stacked images. Or I can back it out a little bit.
The green areas really show up.
I know. Look at this right here. Look at this region.
Uh-huh.
And this one here, this looks like a supernova remnant. Look, it's got almost a spherical envelope around a central bright area. You see that?
Yeah. There's another one up at the top of the image, top right.
Oh, yeah, right here. You're right. That one's there. And we have the one down the bottom that we know about, that we've seen many times. And it's even further down. Here it is. But we got to we have to let these come in first.
Yeah, you have kind of a bridge of stars there.
Yes.
Little to the upper right is center.
Right here?
Yes.
Okay. Is that one of the spiral arms? I think that's one of the arms.
Oh, probably. I just don't remember seeing it that distinctly before.
Mm-hmm. Well, here you go. Look at this, guys. It's beautiful. You see the nucleus of the galaxy really quite cleanly. This beautiful, extensive object here. Probably the equivalent of the Eta Carina Nebula in our galaxy. This one here, something probably even bigger than the Eta Carina Nebula in our galaxy. But these are star-forming regions. You can see other subtle ones here and here. There's many of them in this image that we can see. Wow. Let's do this now.
You can see a lot of the faint stuff around 604 now.
Yeah, look at that. You're right. That's 604 that Daryl's talking about. And look at all these subtle details. We could never see that. In fact, for us, 604 was always this little blob. All right? We could never see all this additional stuff. We could see a hint of it. But now we can actually make out structure. We've never been able to make out structure.
You did something a moment ago where it got a step darker all of a sudden. Can you bring it back like one step brighter?
Yeah, I can do this. This will brighten it up. See, that's brighter now.
Yeah.
I was doing a trade-off between the grain effect and the object. That's all. Ray, the filter in the system is a UHCS filter. I'm not using any of the optolongs. I have the Beta UHC-S. Thank you very much, Renee. That's very kind of you to say for us. Nice detail in here. You can see the blue. Now, the blue are the young hot stars in this galaxy. The young stars tend to be out in the arms of a galaxy, and the older stars tend to be in the middle. They don't go out as much. So let's just drop this down a little bit to kind of soften the noise a little. Look at that. Yeah, it's just spectacular. Notice this string of stars here?
Yeah.
That's fascinating. Wow. That is something else.
I could suggest one more object.
Sure,
see
what
if
do you got?
Can read my mind.
Okay. Andromeda?
Yes. Have you done Andromeda yet with the camera?
I did, and it's beautiful.
That might be a good one to finish the night with.
I thought this was going to finish the night. But you're right. This is really pretty, though, I gotta say. Let's drop this down a little bit. Look at that. Now we are doing this with a moon out, and so these images are still not quite as good as they could be. You know. Hey DPFX, how you doing? Okay. We'll do 19 here. And we're going to call this Measure 33. M33. I'll wait for the 20th. Just beautiful. This is stuff we never saw before. This was a green dot in our last camera. Now we actually have detail in it. It's superb. 20 it is. Saved and saved. Okay, and those colors are actually quite correct now. That's what the colors look like. Let's back out a little just to show the whole thing. Look at that. Wow. Okay.
Ronald asks if you traded in the old camera.
I did not. I still have the old camera. We're going to send it for servicing because of the diagonal streaks that it was showing. Because it's in the camera, there's no doubt. Because we would have seen the streaks on this if it was in the system, in the, you know, the optical system. So I have the same filters, all those things in place. But, so it's the camera. Not sure why. Okay. The last object now, Daryl. The last object tonight. We got to head up a little more north here. And it's the Andromeda Galaxy. Here we go. Now we got to decide what part you want to do of the Andromeda Galaxy, because now we can't see almost the whole thing. Now we only get a segment of it.
Yeah, I kind of figured as much.
Yeah.
I don't think I've seen it yet in this camera.
And you will now. Okay, Andromeda is going to be right there. You want to do the OB association down the bottom right?
Sure.
Okay. So we're going to go a little more to the west. We have Measure 32 right there, which is an elliptical galaxy. Okay, and we go a little more to the west a little bit. Okay. Now, the galaxy, this is the nucleus. And this is going to go all the way down here and trail and go literally off the bottom edge. Alright, so what we can do is just pop that up a little bit. Like that. And that's going to give us the best view of this part of the galaxy. Alright. Alright, so now we're going to do a 35-second shot here. Alright. And off we go. We are guiding. Looks good. And so we're going to our live stack. And you get to see Measure 33. Look at that. Wow, that's really pretty. Holy cow. I mean, and this is all live right in front of you guys. This is just right there in your face. Live in real time. Wow. Okay, here comes the first Andromeda image for this camera. And boom. Wow, look at that. I know, doesn't look like much yet. We haven't color balanced. So we'll color balance now. Now we're gonna do our subtle cut off here. Darken the background. See, when I mentioned before, guys, I said, you know, there's the nucleus, there's the beautiful clouds. This was up there, and I said it'd continue all the way out. It's traveling. The edge of the galaxy goes beyond this. It's several degrees across in the sky. You can already see the hot young associations of stars here. These are called OB associations, O stars, B stars. Okay, in here. And the Andromeda Galaxy is kind of a mature galaxy, and so it has done a lot of star formation in the past, and now it's got several clumps of very intense star formation going on, and that's right in here, for one thing. And then here, there's more at the top on the other side. Oh boy, sorry I yawned. Very nice. Wow, that's just something else.
Ray wants you to go to 0 zoom.
Zero zoom?
What he says.
Okay, if I read him right, he's meaning show the full frame. There's the full frame. You can see it goes right off the bottom. There's more. But wait, there's more. Let's see what else there is.
The bright spot you see left of center, folks, is Messier 32. It's a whole other galaxy right there. It's a satellite galaxy of Messier 31 Andromeda, just like Magellanic Clouds are satellites of the Milky Way.
And there's another one above and just out of shot. It's up top here, called Messier 110.
Yes.
And it's another elliptical galaxy. And the thing about these elliptical galaxies is they just look like balls of stars. And there's very little gas in these galaxies. And almost no dark nebulae. However, in Messier 110, there is a little tongue of dark nebula in this galaxy. It's an interesting galaxy. And with this camera, we probably will be well equipped to image it.
Izabela, per your comment, I like the colors warm and vivid. This displays well the difference between the blue stars and the OB associations out in the spiral arm and the older yellow stars near the nucleus of the galaxy. Yeah. Old and yellow versus young and blue.
Old and lousy versus new and improved. Yep. So you can see here at this end, of the spiral arm, you can see there's all these blue stars here, and then you've got that knot of hot blue, hot O and B star, OB association stars there, and some here, and then there's another group, as I mentioned, at the other end of the galaxy, but we can't show you the whole galaxy at once. On the next telescope, we're actually going to have a rotator, and we're getting a camera that's going to actually guide and image at the same time. It'll work for that one because we're not going to do the hyperstar on that one. So we're going to want to be able to guide, and we're going to have a filter wheel. So we'll be able to do all that we need to do. You'll also notice something here on this image. You see this bright little thing over here? That bright thing right there is actually what's called amp noise or amplifier glow. It's not a bright star just out of shot. And the way you get rid of that is by creating a master dark frame. And that is where you cover the end of the telescope and then take a 30-second exposure at 250 gain, and you average 20 or 30 of those, and that becomes a master dark that you will use for all such exposures. And since we stay in the realm of 20 to 30 seconds at around 250 gain, we could do that and then subtract that automatically for each and every shot, just like we do with our flat frame. And then we would end up having a very perfect frame here. But that said, we don't yet. I didn't make the dark frame. I actually forgot to do the dark frame when I was out there. I'm a bad astronomer, as Daryl says.
You sure are.
Uh-huh. All right. Okay, we'll go to like 15 exposures on this.
Oh, this showed me the one thing I was curious about.
What's that?
You want to shoot M31 now, you're going to have to do a mosaic of it.
Oh, yeah. You probably still won't, your 2 shots won't cover it all anymore. Because we still got more going out the bottom here.
Yeah.
But, well, we'll see. Let's see where this wants to be. Okay.
I've never really noticed the 2 very red stars there at the lower left either.
Oh, here?
Yeah.
Yeah. The other thing people don't understand is that when you look at this galaxy, you're looking through foreground stars. Every singular star you can see is in our galaxy. It's up here. Okay? And the Andromeda Galaxy is way back there, like 2.2, 2.3 million light years away. So we're seeing it through a veil of the stars in our own galaxy. So that's the separation you don't get to see. That's why in the early days they thought that these were spiral nebulae in our own galaxy. But they were not. They were more distant island universes of their own. Okay.
Yep. You can thank Edwin Hubble for that.
Yeah. He discovered redshift as well. Okay. We're going to do the 17th and then we'll be done. Alright, so here is 17. Save it. And then save exactly as seen. And what that looks like is this. This is your full image right there. And that's the free one you can download. If you want the highly processed ones, we make those available through the Patreon if you want to subscribe. Would love to see you join our Patreon. We have a bunch of people that have already joined. That list should be about 100 and 200 people long. So, but thank you to those that have. You guys are amazing and wonderful. You keep us going. All right. I'm going to wait now for the 20 exposures at 35 seconds. Guiding is pretty good, Daryl.
Uh-huh.
Let's zoom in here. I want to show you this. Look at this, guys. Amongst the stars in here, we see these bright OB clusters here. But then we also see every now and then we see a red nebula like this one, another one like this one here, which is really interesting to see. And again, everywhere you look, when you start looking through this galaxy, you see these nebulae. There's some in here, very subtle ones in here. One right there. And I know about some up here as well. There's one right there. And it just goes on and on. Look at this one up here. Right there. That's a fairly big one. Alright. Well, we managed to get to 21. So now we can save it. Save exactly as seen. The color rendering is a little bit off because of the moonlight. I mean, there's literally only so much you can do. It's like you can't knock out the blue sky when you want to take pictures of the stars during the day, for instance. So that's unfortunately what happens here. Same kind of thing. We have these beautiful, beautiful dust lanes as well. Very cool. Wow. Well, there you go, folks. I want to thank you guys for joining us tonight. We will be back, and well, in not too distant future. We will see where we go from here. Let's see. The moon cycle we would probably do something that would take us around having to deal with the lunar cycle. But we'll figure it out. Hey, Creeptasia. Oh man, that'd be great if you'd sign up for our Patreon. We need it, you know. I mean, especially after today, where my whole Facebook profile got hacked and destroyed. Thousands of people gone. You know, every single article I wrote, all the photos I put up there, all gone. Hopefully, I can get it back. Not sure if it'll happen, but we'll see. In any case, you guys have a good night, and Daryl and I will catch up with you on the other side of whatever this is.
Good night, everybody.
See you guys.